So let me give you an example of a differential equation. All right, just a few different forms or a few different types, okay? Let's say I look at 2x plus y equals 4. That's not a differential equation. It's just a linear equation from algebra, right? Now watch carefully. Now it's a differential equation. The only thing that changed was that I put a y prime in there, and now it's a differential equation because it involves a derivative. It has a derivative. So our goal, okay, in solving, see, an equation is meant to be solved, right? So to solve a differential equation, which we just represent by dE, is to find a function y equals f of x that makes the equation true. So we're not solving for a number. It's not like, oh, the answer is 5, right? The answer to a differential equation is the function that makes it true. Okay? So in other words, what we'd be saying over here is, if I take the derivative of some function and add 2x, my answer should be 4. What function makes that happen? So what function do I take the derivative of, add 2x, and get an answer of 4? Right? So that's the idea. Well, before we get started here, let's just think about what y prime would need to be. Can anybody tell me what the value of y prime would need to be so that I would take 2x and add something to get an answer of 4? What would that y prime need to be?
4 minus 2x.
Minus 2x would cancel out the plus 2x, but that would then give me 0 equals 4, and that's not true.
I said 4 minus 2x.
Oh, 4 minus 2x. There we go. Thank you. Yeah. So in other words, negative 2x plus 4 would work. So wouldn't that mean that if I were to take the derivative of some function to be negative 2x plus 4, then adding 2x would get me the answer of 4? So the solution to this differential equation would then be nothing more than the integral. So y, the solution, is just the integral of negative 2x plus 4 dx. So let's look at what our function is. So our function is negative x squared plus 4x plus c. So this right here has the name of a general solution to the differential equation 2x plus y prime equals 4. So this is not any, I mean, this isn't too surprising here, because we've actually solved this type of differential equation already. We've been dealing with differential equations since Calculus 1, believe it or not. We just never called them that. But does anybody have any confusion about what we just did here? So let's take a look at why this works. We're saying that if I were to take the derivative of this function, okay, and add 2x to it, if I were to take the derivative of that function and add 2x to it, I should get an answer of 4. Okay. Well, let's take a look. The derivative of this function is negative 2x plus 4, and the derivative of c is 0. So notice that negative 2x plus 4 plus 2x gives me an answer of 4. Okay, so that's why it works. Well, I'd like to look at this in a slightly different way as well. Okay. What if we were to do this same exact problem, but instead I rewrite this as dy dx equals 4. Hopefully you recognize that this is, what's that?
It should be the same thing.
It should be the same thing. That's very true, because notice that y prime means dy dx. There's no difference between those two. They mean the exact same thing. But it looks a little different, yet it's still a differential equation because it still has a term involving a derivative. Okay? But now we're going to look at this in a little bit different way to see how we're going to solve this and show you that we've actually done these problems, like I mentioned, since Calc 1. Let's go ahead and subtract that 2x to the other side. And we now get dy dx equals negative 2x plus 4. So I didn't have to reason through, like I did up here, I didn't have to reason through what my derivative would have to be. I just got the derivative term by itself. And once I got that derivative term all by itself, I'm now ready to start thinking a little bit more about the fact that if it says that the derivative of y is equal to negative 2x plus 4, then I should be able to solve this differential equation. By doing what?
Integral.
Do that. Yeah, everybody okay with that? Unfortunately, that makes no sense. That makes no sense. I can't take the integral of dy dx, and I can't take the integral of negative 2x plus 4.
You can take the integral of dy and the integral of negative 2x plus 4 dx.
Which is exactly what we need to do first, which is we need to multiply both sides by dx so that the x's and dx's are all on one side. Can anybody recall what I called dx and dy? Anybody recall what I call those things?
Dummy variables, but they aren't anymore.
That's very good. They were called dummy variables because they needed to be there to be able to integrate, but they didn't really serve a purpose other than that, other than to just tell us what the variable was supposed to be. But separately, they actually have another name. Anybody know what together these dy and dx are called? Starts with a D. Anybody?
Differential.
Differentials. These are each separately differentials, which is why we call these differential equations. They just have derivative terms. That's all they are. Okay. So now that I have multiplied by dx, now you can recognize that I can take the integral of the left and the integral of the right. Because in order to integrate, you have to see a dx or a dy attached to it. So this is the process of solving a differential equation called separation of variables. All right, so in order to solve a differential equation, all we're doing is separating the x's and dx's with the y's and dy's. Okay. All right, well, what's the integral of dy?
Why?
Y. And look at what we're about to have, the answer. So notice that all we're trying to do here is integrate this or determine what the function is that makes this differential equation true. And so when I separated the y's and x's and integrated, I now get y is equal to the integral of negative 2x plus the integral of 4 plus c, and sure enough, that's our solution. All right. Everybody cool on that? So this is just the real brief, basic, simple introduction. It actually is not just an introduction, I guess. It pretty much taught you everything you need, but it's not really the full extent of differential equations yet. So I wanted to just write out a few other differential equations, okay? So maybe other differential equations. We're not going to solve all of these, but I just want to maybe demonstrate a few. Okay. Let's say I have y double prime minus 6y prime plus 7 is equal to 0, or 7y even is equal to 0. That's a differential equation, which is basically saying if we take a function, multiply it by 7, subtract 6 times its derivative, add on its second derivative, all the terms should cancel, and I'll get an answer of 0. What function makes that happen? We're not going to solve any of these until the class differential equations. Okay, all I'm doing right now is just giving you other forms of differential equations. Differential equations are nothing more than just functions that have derivatives in them. Okay. How about another one? How about x squared y double prime minus 3xy prime plus 2y is equal to x cubed e to the x.
That's a fun one to just pull out of your head.
Yeah, thank you. This one right here is just basically saying, hey, let's take some function. That's going to be our solution, whatever y is, that's our solution. Take some function and double it. Then take its derivative and multiply it by negative 3x. Then take its second derivative and add x squared. And when I do so, I should get the function x cubed e to the x. What function makes that happen? That's the purpose of the class differential equations, is to teach you methods of solving all of these types of differential equations. We're only learning one in this class, and that's separation of variables. Okay? So this is just kind of an introduction to differential equations. They could show up in all kinds of different forms, okay? But what I'd like to do is just verify. I'm going to tell you an answer to one of these, okay? Is y equals x squared a solution to this differential equation? Okay, any ideas on how I can determine whether or not this is?
You could find the first and second derivatives of y equals x squared.
Yeah, absolutely. And that's exactly what we should do. We need to be able to plug these derivatives in to see if it's actually going to work. So y prime is 2x. Y double prime is 2. So that would mean I could come over here and plug in y double prime minus 6 times y prime plus 7 times x squared. And that should be equal to 0. So in other words, is 7x squared minus 12x plus 2 equal to 0? What do you think? What should we do now? Well, it's a quadratic equal to 0. So what do you think you could do?
Quadratic
Right,
formula.
factor.
You could factor it maybe. Maybe I could factor it. If I can't factor, then use the quadratic formula, right? But the problem is that this is automatically false. No, it is not equal to 0. Because in order to be a solution to a differential equation, it must be true for all x's, not just some x's. So what we mean is that when I plug in the second derivative, the first derivative of the function, everything better cancel to become 0. The problem is that didn't happen here, and therefore, even though this might be true for some x values, it needs to be true for all x values in order to be a solution. Okay, so the answer here is no. It is not. Okay. Well, let's try another one. Okay. What about y equals e to the x? Okay. So I'm going to go ahead and separate you guys into some groups here. And do the next couple, just the same differential equation. I'm going to give you a couple though. What about y equals sine x? Let's make this e to the negative x. Okay. And give me another function that it looks like might work.
Y equals 0.
Sure, y equals 0. See if y equals 0 works. So I'm going to do that one really quick here. Because it turns out that y equals 0 is often called a trivial solution. Because it's a solution that you would that works automatically just for the sake that y prime and y double prime are all 0. So when I plug those all in, 0 minus 0 plus 0 is definitely 0. Okay. And so we could see for y equals 0, this is going to be a solution because we see 0 minus 6 times 0 plus 7 times 0 equals 0. So the answer here is yes, this is a solution. Okay, but it's a trivial solution because it's a solution that we wouldn't ever get through the course of doing or using some methods to solve. It's something that we have to look at and reason through in order to solve. I'm going to give you one. I'm going to give you one more here. What about y equals e to the x, or e to the, make it e to the 3x. And how about y equals e to the 7x? Now, does anybody maybe see why I keep choosing a bunch of exponential functions for you to try? Why might I be choosing exponential functions to see if it's a solution for this differential equation right here?
Since the derivatives stay relatively the same, they should cancel out.
That's right, because derivatives of exponentials are other exponentials that look very similar. So it would seem reasonable that the solution to this would probably be an exponential function. I just want to see whether or not these are going to be solutions here. So go ahead and pick y equals e to the negative x, sine x, e to the 3x, and e to the 7x. All right, so this was the original differential equation, y double prime minus 6y prime plus 7y equals 0. So let's just go through a few of these. So y equals e to the negative x. So we just had to take a few derivatives down here, right? And when we plugged those in, we got e to the negative x minus 6 times negative e to the negative x plus 7 e to the negative x. And they're all e to the negative x type terms. So it seems like an e to the x type of function would make this work if I had the right exponent, right? The problem is this gives us 14 e to the negative x, so that didn't work. So then you go to y equals sine x. Well, you might notice why sine x definitely isn't going to work. Because the function is sine, the second derivative is sine, but the first derivative is cosine, and there's no way to combine those sines and cosines together to somehow equal 0. So sine x definitely is not one of the solutions. We did y equals 0. What about e to the 3x? Okay. Well, e to the 3x has a derivative of 3e to the 3x, which has a second derivative, sorry, y prime and y double prime, which has a second derivative of 9e to the 3x. So if I plugged those in appropriately, I got negative 2e to the 3x. Again, not all the terms canceled. And it turns out that e to the 7x doesn't work either. Because this would be an e to the 7x. And notice that this would be 49 e to the 7x minus 42 e to the 7x, which is 7 e to the 7x.
You got me.
7 e to the 7x, which gives me 14 e to the 7x. So none of these were, and this was because I screwed up. But this was a good exercise in verification, so I think you've got the idea about how you verify if something is a solution or not. But that's because I wrote the problem wrong. When I was writing it down, I meant to write minus 7y. So let's just see if it did say minus 7y, how that would affect things here. Because e to the negative x should have been a solution. Because what if this was a minus? And that was a minus. Notice I'd get 7e to the negative x minus 7e to the negative x. And that, sure enough, would have canceled. Then you go down to e to the 7x. What if instead of it being plus 7y, it was minus 7y? Look at how that would change things. We'd get 7e to the 7x minus 7e to the 7x. So there is a method of solving this that you're going to learn in differential equations. But right now, we're not asking you to solve all differential equations. We just want you to be familiar with what it means to be a solution and how to verify whether or not a given potential solution is in fact a solution. Okay? Are we cool with that? So let's solve y prime minus 2xy equals 0. Okay. Well, the first thing we tried to do, the only method that we're ever going to use in Calculus 2 to solve a differential equation is to separate variables. So the first step we have to do is we have to convert y prime into dy dx so that I'm going to be able to separate the dy's and dx's on two sides. And secondly, let's move that other term over to the right side. Because now, in order to solve, I want my dy terms to be over on the left. And I need to get that dx out of the denominator. So that means that I'm going to need that dx to come over here. So I got to figure out what I need to do in order to make that happen. Well, first of all, I need to multiply by dx. Right? And then I can see that I have a 2 and an x and a dx that are totally fine to stay on one side. The problem is that I can't have that y on the right, so I have to divide by y in order to cancel it out from both sides. So let's look at what I have. So we could see that the dx and the dx cancel, the y and the y cancel, And so all we're left with is 1 over y dy is equal to 2x dx. So our main goal in solving a differential equation is to separate the variables. So we've now separated, and now we can integrate. So here we get the integral of 1 over y dy. Well, you can obviously see, again, another reason why integration is so important to know how to do, right? I mean, every time we solve a differential equation, you're going to be solving by integrating at some point or another, and you're going to be integrating all kinds of different types of functions. So the integral of 1 over y dy is the natural log of the absolute value of y. And the integral of 2x is x squared. Now notice that technically this has a plus c over here, and this has a plus c over here, but they're technically different. So I could call it C1 and C2. But really, I could just subtract C1 from both sides. So doesn't that mean that I really just have a constant on one side now? So the standard way to do it is just don't even bother to do that on both sides. Just put the plus c on the x side. Okay? So I could really just bypass this whole step right here by integrating the left side, integrating the right side, and just put a plus c on the right. Now this right here is technically the solution. This is the implicit solution. Whenever possible, we should always try to solve for y. So that's why we're going to take it a step further. And we're going to take e to the power of both sides to get rid of that natural logarithm, which now means that we get y, the absolute value of y is equal to e to the power of x squared plus c. But you got to realize as well that e to any power can't be negative. So I technically don't really need to write the absolute value of y in this particular situation. And so notice I could just write y. But there's another little trick here. Because anytime you have an exponential where you are adding c, you could actually rewrite this by the properties of exponentials as e to the x squared times e to the c. Because wouldn't I combine these together by adding the exponents? But notice that e to the c is a constant. So why don't we just call it something else? Like, I don't know, C2. But if I do that, I should probably go back and start calling my prior constants something else, C1, C2, whatever. You don't really need to. And at this point, we finally get our solution, which the best form of it is C times E to the x squared. Keep hitting my...
Is there
Okay.
a specific term for this kind of solution?
Yes, there is. It is an explicit solution. So the reason we call it an explicit solution is because we have explicitly solved for y as a function of x. This up here is implicit because of the fact that we haven't really solved for y. And in fact, some differential equations, you're not going to be able to get y by itself. So you just leave it as is. But whenever you're algebraically able to get y by itself, you should always try. Okay. Cool.
Is this Calc 3? Like,
This is
Most
differential
variable.
equations. I mean, this is calculus 2. I mean, we're learning it now. This is a part of the curriculum for calculus 2. Calculus 3 deals with multiple variables or multivariables. This really still only has 2 variables, x's and y's. Okay, so let's just kind of recap what we were doing here. This is an application of integrals, which is why it's in Calculus 2. So we're starting with this differential equation here. And we're saying that there is some function, I don't know what it is, but there's some function that if I take the derivative of the function and I subtract 2x times the original function, those two terms should cancel and I should get 0. So all we've done here is we've just figured out, well, why don't we separate the variables? And when I separate the y's with the dy's and the x's with the dx's, I can integrate both sides and I now get this solution. So from this point on, it was just a little bit of algebra to get y by itself, okay? With this clever little trick, I guess, when you see e to the x squared plus c, we wrote that as e to the x squared times e to the c, which was just some other constant. So we just made it look, oh, by the way, I screwed up here because this should have been e to the x squared times c2. So c2 is what I should be writing right here, okay? But remember, C2, C, it's all some constant. Some instructors will just allow you to say, just replace C with another C and then say, oh, that's e to the c, replace it with c. I don't like to do that, having taught differential equations, because all of the c's that we deal with in a problem are all different. So I want to make sure that we're aware that these are different values. So I'm just calling them different constants. So why don't you go ahead and get back into your groups and verify that this is a solution. Now I say a solution because I have C2. C2 could be anything. So 3e to the x squared is a solution, 5e to the x squared is a solution, negative pi e to the x squared is a solution. No matter what the constant is, it's a solution. 2y prime minus 2xy equals 0. So we just want to verify that this is in fact a solution. Okay, so I'll throw you into your rooms and call you back in a minute. So this was a pretty simple one to verify here, but you just had to use the chain rule to differentiate, right? So the derivative of c2e to the x squared is c2e to the x squared times an extra derivative of x squared. But if I plug those into the appropriate spots, notice that the two terms become the exact same term. So they subtract to give me that 0 is equal to 0. And so sure enough, it worked. And it's a solution, which means that I solved it correctly. Okay. Now, the last kind of thing that I wanted to discuss here is that I mentioned earlier that this has another name, okay? This has another name, if not just an explicit solution, but the general solution as well. In fact, even explicit solutions are general solutions. It's a general solution because it has C. If it didn't have C, then it wouldn't be a general solution, it would be a particular solution. But the only way to get a particular solution is if I find the value of C. Can anybody think about what I would need to know if I was told, if I needed to find the value of C? What would I need to be given if I'm trying to find the value of C?
An interval?
An interval? Well, what would an interval tell me in order to find the value of C? This is just an equation, and I'm trying to find C.
An ordered pair?
I would need to know an ordered pair. Wouldn't I need to know an X and a Y? So I'd like to go ahead and go to Desmos real quick and type in this c e to the x squared here. We're going to add a slider at c here. And so this right here is the solution to this differential equation. But let's look at what happens as I modify c. What happens as I modify c, do you think? What's going to happen to this graph?
It'll get steeper, shallower,
Yeah, it's a
or
stretch.
change
So
direction.
I either stretch it. It appears that you know, if I should zoom out a little. It appears that what's happening is that it is moving up and down, but what's really happening is it's stretching. It's stretching, getting narrower, and as it gets narrower, it's moving up and down the y-axis here. But notice that there are lots of solutions. This right here is a solution to the differential equation. This is another solution to the differential equation. This is another solution to the differential equation. So is this right here. That's another solution to the differential equation. But what if I told you that there was only one solution that was going to go through the point 0, 5? Okay. Well, this obviously 10e to the x squared is not going to be the solution, nor is 3.1e to the x squared, nor is negative 4.7e to the x squared. It looks like there's only one solution that will touch that point. Let's see, it's almost there. Almost there, it's getting there. Oh, and it looks like it's 5e to the x squared. So what we are told here is that if 0, 5 is an initial condition, we could plug that initial condition into the general solution to find the c value, which would then tell me the particular solution. So I know it's a lot of terminology here, so I'm going to go through this a little slower. Okay. So what is the solution to y equals c e to the x squared? Nope, that's wrong. To y prime minus 2xy equals 0. That passes through the point one E. All right, well, we don't have to go through this whole thing again because we already found what the solution is, right? We already know that y equals c e to the x squared is the general solution. Okay. This point right over here is now referred to as the initial condition. So what we're going to be able to do at this point is use that initial condition to find the unknown constant of integration right here. Okay. So why don't we do that? So we just plug everything in. We get y is equal to e equals c times e to the power of 1 squared. So e equals c times e. So 1 equals c. Okay. All right, well, we've just found something else then. So we've just found the constant of integration. So we found a particular constant that's going to be needed in order to pass for that differential or for that solution to pass through the point 1e. And with that value of c, we're going to now be able to write the particular solution. Since the coefficient is just 1, we could just write it as e to the x squared. And what we've just found is the particular solution that passed through the point 1e. So look at the difference between the general solution that still has the unknown value of c and the particular solution which doesn't have c anymore since we used the initial condition to find it. Okay? So yes, you should know these terms. Okay? Everybody cool with this idea here? So again, the understand that, and by the way, maybe I should tell you the last term you should know, which is really the first term you should know, that this thing right here is the differential equation. So this terminology just gets you to be proficient with the way that you're actually talking about these things. So when I solve a differential equation, I get a general solution. If I was given an initial condition, then I could plug the initial condition in to the general solution to find the constant of integration, which is c. Once I know the constant of integration, I could plug that constant of integration into the general solution, which would then tell me the particular solution. I mean, they all make sense when you actually start thinking through why they're called what they're called, but you should definitely know the terminology.